All right. So before we get started, I have a couple notes up here. One thing I just want to remind you about when you're dealing with linear mixed effects models is that when talking about between subjects versus within subjects, factors, variables, basically what you're talking about is fixed and random effects. And just wanted to remember that, or remind you that when you're told to fit some model, like you just have to stop and think about whether or not something should be included with the random effects, basically. You know, for instance, here we have the, whatever dB predicted by variable 1 and variable 2, but variable 1 is a between subjects factor, so you don't put that in the random effects. You know, perhaps variable 1 is gender, and why would we not include gender as a random effect?
Because presumably your gender would be the same.
Right, exactly. That those random effects are when, the participant is exposed to both conditions. And so just wanted to reiterate that. Today we're going to be working with this behavior data. Let me go ahead and read that all in there. And so basically what this data is looking at is we have their ID, gender, age, whether they're single or married, student or non-student, what their religion is. This is the extent to which they're religious. This is the each participant rated 10 behaviors. They rated their reaction to each of these 10 behaviors, how frequently they perceive these behaviors are engaged in, and how deviant of a behavior that is. And then again, behavior ID is just like which behavior was it. And so basically what these researchers are wanting to see is like what predicts somebody's reaction to some deviant behavior. Is it how often they think this behavior occurs, how bad they think this behavior is, et cetera, et cetera. And so when we look at the summaries, we can see that we have, by calling the unique IDs, we have 72 participants, 720 observations, which lines up with the 10 observations each. Here I have this thing from Lattice, which is making the individual plots kind of like we've made before. I went ahead and included this just to make a point, and then I talk about it here in this note, that if we use ggplot the way that we've done before to make the exact same plot, I just wanted to point out that there are, as with everything else in R, that there are multiple ways to accomplish the same thing. And even though when you look at this code, you see that the ggplot code is a little bit longer to write, I personally, I stick to ggplot for everything because it just makes life that much easier, because there's not really much of anything I can think of that ggplot can't do that other things can, but there is a lot that ggplot can do that others can't. And by sticking exclusively within ggplot, I'm always working with the same calls, the same arguments, the same functions, the same layers. And so if I did want to customize some graph that I was making, if I'm using Lattice's XY plot and telling it, basically this code is just telling it to group it by ID with this little portion of the code here. And if I wanted to customize that, I wouldn't know how. I'd have to get into the help files and figure it out. But with ggplot, because I use ggplot for everything, it just makes life easier. So just wanted to make that point as well. To start today, we're going to start by working our way through making a spaghetti plot. All right, so we're going to make a spaghetti plot that is just predicting participants' reactions from the perceived deviance of some behavior. So we make that model called plot mod, And then if we look at the random effects by pulling out this ranF function here, we see that for each participant, it gives us the intercept and the slope of deviance for the intercept and slope of that random effect.
So why, we have like 90 some odd of those. I thought there was only like 72 participants.
Oh, no, because look, it's not, it's 1, 3, 4, that's the participant number. So there's only, yeah, it's the ID, not row number. So this is the information that we'll need to make the spaghetti plot, or part of the information. But if you look at the structure of that, you see that the ranF, even though here on the console, it kind of looks like it outputs, like a data frame with columns, it actually outputs a list. And you can't put a list directly into ggplot. It'll yell at you and tell you that it needs a data frame. And so, even though this is a list of only one, it's a list of a data frame, but the data frame is this ID right here. So in other words, here what I want to show you is that, like, if you're like, oh, well, we'll just wrap it in data frame. And so we do ranF plot mod wrapped in data frame and call it let's check this. And then when we look at let's check this, you can see that, like, that didn't turn out the way that we wanted it to. Like, we just want those two columns as they appear in the console. So when you look at this structure and you see that it's a list of one and the first list is called ID, you can call that specific data frame from the list by using ranF plot mod and calling ID with the $ID. And, again, it'll pull out that data frame. And so if we store that as plot RE for our random effects, and now we check the structure of that, now we have a data frame with those two columns with each of our intercepts and slopes for each participant's random effects. But you'll notice that in this data frame, the column, the variable name is open parentheses, intercept, close parentheses. And so here I'm just reminding you that in R, you can't have leading special characters or numbers in your variable names by default. You can get around that by using these accent marks, which is not the apostrophe that's the same as like the quotation marks button, but rather the accent mark that's up next to the one key, the same key as the tilde, but without hitting shift. So if you put those on either side, like, you can have whatever you want as the variable names, and R will recognize that, like, oh, this is some sort of name, not, an operational parentheses or, a number, whatever. But I'm going to get around that and just rename the columns. So in my plot RE data frame, I now have my random effects intercepts, RE ints, and random effects slopes. And so now we have our random effects slopes and intercepts that we'll use for the spaghetti plot. But for the spaghetti plot, we want to plot each participant's random effects, like in gray, and then the fixed effect overall from that model in black. So we also have to call our fixed effects using fixed F plot mod, and it will give us the intercept and slope of the fixed effect. Then here, just reminding you that you can index and call specific values from that. So if you run this first line with fixed F plot mod and then in brackets 1, it will call just the intercept from the fixed effects, and the fixed effect plot mod 2 will call just that slope for deviance. So now we have all the data that we need to make the spaghetti plot. We're using that one fixed effect and each participant's random effects. But one thing I want to point out is when we look at our random effects intercepts, these are not the actual raw values of the intercept for the participant, for instance. So let's say that we have some model with an intercept of 1. Nice, easy numbers. And then in our random effects intercepts data frame, this participant here having an intercept of 0.03 does not mean that the intercept of their random effect is actually at 0.03. Rather, that means it is 0.03 away from the intercept of the fixed effect. So if the fixed effect intercept is 1, then the actual intercept of this participant's random effect is 1.03. Or if it's a negative number, this participant's intercept would be 0.91 or whatever. Like, so you get what I'm saying? That like the RANF doesn't give you the actual raw values. It gives you the difference from the intercept of the fixed effect and the difference of the slope from the fixed effect. So what I'm saying here is, remember that you have to add these values together in order to actually have like the raw units that you could plot on there. Now you can go about this one of two ways. You can either, we've done this before where back at the beginning of the year, we did some plots by extracting the slopes and intercepts, and like you can just add them together inside ggplot and say, add the random effects intercepts plus the fixed effect intercept. Or if you wanted to, you could just add the fixed effects intercepts to the random effects data frame and just change those numbers and put that in the plot. What we're going to do today is just do them in line. So we're going to start with just setting up our initializing the graph basically, which I always start with ggplot and theme classics. I know that's what I'm going to want anyway. And now from there, we're going to use geom AB line, which is the one that instead of saying, x equals y equals, the arguments that you put in is what's the slope and what's the intercept. So we have geom AB line, and we'll have our data equals our plot for random effects. And then we have intercept equals. So now remember, our intercept is each of these values plus the intercept of this fixed effect. So if we just copy this up here and say the intercept equals the fixed effect intercept plus RE ints. And then the other piece of the equation that we put in is the slopes. So slope equals the slope of the fixed effect plus RE slopes. And now if we run that, because these need to be in an aesthetic. Because I'm calling information out of a data frame and not putting in raw numbers. Hey, how about that? Now it worked. All right, so as you see, like just from this initial thing, it's like, what the hell is going on here? Yeah, what's up?
So if you do plot.re, money sign, the RE hints.
Yeah, that
works. Is there an issue with doing that versus AES here?
No, that should work in theory. The only difference is that Well, and if you are using the dollar signs, you wouldn't need to say that data equals plot RE. Because then you're explicitly calling something instead of saying, oh, you'll find this information in wherever I say data equals whatever. But the reason that this looks all weird right now is just because we haven't defined our X and Y coordinates. And so like our graph isn't centered and such. So let's go ahead and throw that on there. And we'll say that scale Y continuous, and we'll define our limits, which is telling us what's the min and max of our Y scale. And let's just define that as -5 and 5, which I got that information just from messing with this graph, and I happen to know where that is, but you literally just pick some numbers and play with them until you get something that says like, oh yeah, that looks like it shows the information that I'm trying to capture. So if we change our Y to, you know, +5 to -5, but again, like it still looks weird, and that's because we haven't defined our X axis. And let's define those limits as plus and minus, or negative and positive 10. All right, so now at least like we have something that resembles something that we should be going for. Now from here, I'm going to go back up here to this geom AB line, and I'm going to add a couple additional arguments, because for one thing, we want our fixed effect to be black and the others to be gray. So I'm going to change our color up here to gray. And I'm also going to adjust the alpha and make it 0.5, so that way we can see that, you know, it gets darker where there's a lot of overlap and things like that. Cool. So now we have our random effects are plotted. And the only thing left to do now is to plot that fixed effect line, which is, you know, also another geom AB line. Only this time, we're only plotting the fixed effect, so we don't have to worry about adding anything. And we can say our intercept equals, calling the intercept from that fixed effects. And then down here, we'll say our slope equals that slope called from the fixed effects. And now we have our fixed effect line plotted on there as well. And then from there, you know, you would say, for instance, labs, and you define that your x-axis equals deviance, and y equals reaction, and et cetera, you go on from there. But this is the basic spaghetti plots. Like what you're expected to be able to produce is extract those random effects and plot a line for each random effect for each participant, and then overlay the fixed effect on top of that. Now, unsurprisingly, as your models get more complicated, graphing them becomes a lot more complicated. So this is not something that we're going to expect you to do, but I just want to show you why and how, that way at least you have an idea, because this is the type of modeling that's likely to come up in your studies. This is something that's commonly used in our field. And so I at least want you to have an idea about like, oh, hey, this is possible. I might have to sit down and figure out how to do it. But so here I'm just making another model that I'm predicting the same thing, but I'm adding in frequency. And same thing, extracting my random effects. And then when we look at our random effects here, we can see that now we have, for each participant, their random effects, their slope or their intercept, their slope for deviance, and their slope for frequency. But each one of these is unique, and so you can't really plug that in. And so the long story short of it is that really and truly, even though it seems a lot more complicated, it's not, once you realize that it's the same way that we've made graphs all year that when you have, if you have a categorical variable, it's easy. You just plot these things and then facet it by this categorical variable. So you'll have two spaghetti plots, one for the control condition and one for the experimental condition, or whatever that case may be. If you have a continuous thing like frequency, then you just decide on what values you want to visualize, so whether that's plus and minus 1 standard deviation or whatever, and you would basically set your frequency to like plus and minus 1 standard deviation, generate 2 sets of random effects, and plot them on separate plots. So as far as like trying to get the actual, continuous deviance, continuous frequency on one plot, like that's not a thing. It's not what you would do. Instead, like you would just have to decide what is it you want to visualize, break it down into, whatever values of one of the continuous things you want, and then you can facet and have multiple spaghetti plots for different values of whatever that continuous variable is. Does that make sense? But again, like, we're not going to be asking you to make spaghetti plots across multiple variables for the homework or exams. All right, and then I'm going to go back up here and rerun this because we'll talk about it here in just a minute. All right, so the same model that we ran for the plot, just predicting their reaction based on how their perception of how deviant the behavior is. And so we have 2 fixed effects for this model. We have the intercept and the slope deviance. I'll let you go through later if you want and read through all of this in more depth. But to summarize what it's talking about, what's different about these linear mixed effects models? Actually, let me ask you, what's different about these linear mixed effects models compared to what we did last week with the repeated measures? I'll give you a hint. It has to do with the number of observations.
You have 1 of 2, so you're introducing error.
Exactly. When we talk about that there is a new source of error when you're working with linear mixed effects models, it's because last week for each participant there were only 2 things. And no matter what these 2 values are, you can always draw a perfectly predicted line between any 2 points. So it's kind of like, we've talked a little bit about overfitting and things. That's basically what it is. Like you perfectly fit a model to each participant when there's only 2 points. But now you can see that like there is some error. So if this is the predicted line, like there's some error in that line. So that is what we're talking about when we say that there is now some additional source of error in your model when you're doing linear mixed effects models. It's because there are, if they only rated 2 behaviors, we'd be back to an error-free prediction because, again, you can draw a straight line between any 2 points in space, no matter where they are. So blah, 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 explain more of that. So as far as what that means for our estimations is that once we have more than 2 measurements, we are departing general linear model territory, and we are getting into maximum likelihood estimation territory. So kind of like we talked about that a little bit when we were talking about the generalized linear model and logistic regression and that sort of thing. We're now, instead of minimizing the sum of squared errors, we're trying to maximize the likelihood of the parameters fitting the observed data. So just as to kind of walk through, well, and really all you need to know is that in doing so, you bias your estimates. So here, if I just call the coefficients of that model that we created, which has maximum likelihood estimations, that's what these are. These are the maximum likelihood estimated intercepts and slopes. And if we take the means of those intercepts and slopes and we get 0.57 and 0.60, if we look back at our output, we'll see that the fixed effects were the average of the maximum likelihood estimated, slopes and intercepts. By contrast, Elmer has a function called LMList, and basically what this does is we tell it to run a bunch of individual ordinary least squares, OLS regressions, which is the typical. So what this code right here is saying is to regress reaction on deviance grouped by ID. So this is basically the same as saying, hey, take this data frame and select where ID equals 1 and regress reaction on deviance and give me a slope and an intercept. And then where ID equals 2 and do this again. So it's kind of a way of quickly but manually doing just a regular LM model instead of the maximum likelihood. And so if we run that, now when we look at our slopes and intercepts, with the same reaction regressed on deviance, this is our intercepts and slopes based on ordinary least squares, so just typical LM regressions instead of the maximum likelihood. And when we look at the means of those, we'll see that that gives us those different means. And so when we do the OLS regressions, the means no longer give us those fixed effects estimates because it's a biased estimate. So all of that basically to hammer in the point that now that we have introduced this additional source of error, that's why we switch to maximum likelihood estimation instead of minimizing the sum of squared errors, because we don't want to end up with biased and incorrect estimates. Does anybody have any questions on what we've talked about so far?
Or your coefficients output of that last OLS mod, it has in A's of 93.
Mm-hmm. Because 93 is missing.
Could that be an issue at some point?
I mean, yeah. I mean, any sort of actual analysis that you're doing, like part of the explore your data, like it should include things about looking for missing data and things like that. One quick way that I talked about last semester, what I use whenever I'm working with my data, there's the package called Amelia, and it has a function called mismap. And so if you just say Amelia mismap data frame, and it outputs like a big plot that shows cream colored things for things that aren't missing, and it'll have like a little red mark for things that are missing, so you can very quickly just look across all your data and see what's missing here, and is there something that's systematically missing, or does it kind of look like it's just they didn't give me this measurement here, they didn't give me this measurement here, or oh, a lot of people decided not to answer this particular question, and that sort of thing. So that's just part of good data hygiene, is being aware of what all's missing at least. As far as how to deal with that missing data, that's its own entire thing. As far as do you just take out participants who are missing data? Is whatever you're doing something that you can just ignore the missing data and it's not going to mess up anything? Do you need to impute the missing data somehow or another? And if so, what method do you use? And there's no consensus and 1,000 different ways to do it. And so, yeah, dealing with missing data is its own entire category, and that's just not the focus of what I'm working on today. So,
just a quick question on that though. So I mean, I'm kind of familiar with some of the imputation stuff. and I mean, it's really cool the way it works, but I was curious, is there like consensus over like how much missing data is too much to use a method like that?
Consensus, no.
I mean,
There are some, I mean, different people have different rules of thumb about how much, because I mean, part of it has to do with, well, like not just how many are missing, but like how many participants are there, because your threshold for like what's concerning versus not, you know, may be reduced at, if you have a data set that you have, you know, 6,000 people, are you going to be upset that you have like 50 people missing? Like, no, for like this one particular variable or whatever. But like I mean, there's really not a good answer, because the answer is like, no, there's not a consensus, because even among then, whether or not, like, so we have some missing data, what do we do with it?
Yeah.
You know, and then as far as the imputations go, some people will argue that, you know, all right, so you have some variable. Let's say you have like a 10 item scale that you're asking to measure some construct. And, you know, somebody's missing, you know, 2 of these questions. Some people will argue that they think that you should impute it with like the mean of that variable as a whole, like across the entire data set, just put in the mean value for that variable. Others might say like, no. If these 10 items are measuring, you know, this construct, then the best prediction for what these missing values would be to take the mean of the other 8 items for that participant and fill that in instead. And then others might say, yeah, but there's this manipulation, so we're expecting this to move, so we should fill this in with the mean based on everybody who's in this condition, or this. And then aside from that, like, mean filling is not the only way to impute data. That you can do multiple imputation, where basically you take any other number of factors and generate, you know, a linear regression and say, well, based on everybody else's, what their values were for this, and then what their values for these other variables were, like the best prediction is this. If you're interested in things on the imputation side, there's a package called MICE. It's multiple imputation and chained equations. That it is an extensive imputation library. And if you look that up, I'm sure on like ResearchGate and Stack Exchange, things like that, like you can find a lot of very involved, sometimes heated, we'll call them debates on like what's the proper thing to do in any given situation. But it, unfortunately, like it wildly varies from like analysis to analysis. That's about the best answer I can give you.
I imagine there were some sort of like professional standards that.
No.
You don't want to know if you're like taking too much liberty.
No.
Math behind it, because,
You know, there's, I'm trying to remember, I can't remember his name. There's a book called Statistics as Principled Argument. And it's a great book just as far as like kind of the philosophy behind, you know, how you should approach analysis. And ultimately what I say is that ultimately what it comes down to is like, what do you think? And just knowing that there are these different things, and being able to look into the decisions that you're making, and at least knowing that like, yeah, by doing this, like I may be, you know, regressing my data towards the mean, or I may, you know, have this or this or this, but, you know, there's no one right way to do it. And so like, I know at least what mine is doing, and I know that like, yeah, some people might have a problem with that, but like, I am now justifying to my reviewers and to my readers and saying like, this is what I decided to do. Here's why I decided to do it. And I think that it's the right decision to make. If they disagree, like a reviewer will tell you, well, I disagree. And you may have to argue with them individually, or put in a footnote or a caveat of some sort and blah, blah, blah. So ultimately it just kind of comes down to, for the specific situation that you are in, like, what can you justify and what arguments are you going to make to say, like, this is the decision that I made, here's why I made this decision. And if somebody else disagrees, like, okay, so we don't agree on everything. We don't have to agree on everything. You know, if you do make, you know, some BS arguments, they'll call you out on it right quick, and you know, that's that. But ultimately, it just comes down to, like, what are you going to justify, and what do you think is best in that case?
Cool, thanks.
All right, so down below, I just put in some stuff with saying to, all right, like, make a model that does blah, blah, blah. And y'all just fill in the Elmer to create that model, run the summary, and then take a second to interpret the intercept and slopes of your models, and try to, at least to yourself, put those into words. I'm here if you have questions, and then you know, we can talk about those interpretations and whatnot as you'd like at the end of class. Yeah, so just work on those models there at the bottom.